Okay, everyone. Hi. We've met. So a couple of people that don't have the chairs will be there in a minute. We didn't expect that to be so biased towards the beginner's track, but we'll figure it out. So the first speaker is Julie Moronuki. She came to us from a land far away. And she'll be talking about Haskell.
Hopefully, right? You're all aware that this is the beginner track, right? Because I'm looking at some of your faces and I know you're not beginners. So yeah. So I think you're sort of having a little joke here. So I was looking at I proposed to talk about to do a gentle introduction to profunctors, and because I don't actually think that that they're as difficult or that they need to be as difficult as they were for me when I first encountered them. So I proposed to do this, and I proposed to start with the type system and then work through an understanding of what different kinds of functors are and what a functor in general is, and then work our way up to profunctors, sort of building up from a very small foundation. And as I was looking at the schedule of what the other beginner track speakers were proposing to do, several of them said that you didn't need to come with any knowledge of Haskell yet, that they could take you from zero knowledge of Haskell to whatever their particular goal was. So I thought, okay, well, I probably need to start from that same foundation then, because then people who are coming to the beginner track are probably expecting to come with not being able to not know any Haskell. So how many of you in here actually don't know any Haskell? All right, good. We actually have some people who don't know Haskell. That's awesome. That's awesome, because some of you today in particular, because I am starting from a foundation where you don't really have to know much Haskell. Some of you today who do might be a little bit bored. Tomorrow we will be talking more about functors, and on day 3 we will talk about profunctors specifically. So if there's anybody who sees the title of this slide, Types and Functions, and maybe what the first slide is, if you think, oh God, yeah, I'm going to be way too bored in here, and you want to go ahead and go learn about linear types, that's okay. It's not going to hurt my feelings. All right, but we are starting from a foundation of maybe you don't know any Haskell, so hopefully everybody will be comfortable. Okay, so today I said types and functions. We're going to talk about the function type, but we're not actually going to have any functions at all. All we're talking about is type signatures, so I hope that you are excited about type signatures. All right, so in Haskell, all data has a type. Everything, all of it. And sometimes it's not what you expect. So when we put something in quotation marks, like the word Julie, and we find out the type of Julie, we see that it is a list of characters. It is also known as a string, but string is a type alias for a list of characters. But see, and now there are chairs. So this worked out great. It's okay. It only hijacked it for half the room. The other half is still fine, so. All right. So a string literal, then, such as Julie, has the type list of characters. And a numeric literal, such as 5, has this, where you might be expecting that it has the type such as integer or int or something that looks like what you would expect a numeric type to be. Instead, we have this. We're going to talk more about what this constraint here, what the num a, the fat arrow part, means. We're going to talk more about that as we talk through reading type signatures. But this means that it hasn't yet, it hasn't yet decided what type 5 is. So For now, 5 is going to be as polymorphic as it can be until we have to decide what type it is. So for now, the only information we have about 5 until we use it in some function where we can tell then what type it must be, or until the compiler forces it to default to integer, then for now we just know it's some numeric type. That's what the num stands for, as you might guess. Okay. Variables with the same name must have the same type. So this is the type signature of a function called ID, which is the identity function, which takes one value of type A and returns a value of type A. And we have const, because you always have to, if you're doing a Haskell presentation, you always have to have ID and const in there somewhere, I'm pretty sure. And it takes a value of type A and a value of type B and returns a value of type A. Now, these two types can be anything because there's no constraint on them whatsoever. So the A and the B could be any type at all. We know nothing about these types, except for that the A in the identity signature both must be the same type, and in the const type signature, the B could be a different type from the A, but it might be the same. We leave open the possibility that it's a different type, but it could be the same. Okay, when an argument must be a function, because any of these, so for example here, the A to A and the A to B to A, any of those A's or B's could be a function, because function is just another type in Haskell. And so one of the possibilities that those type signatures includes is, for example, with identity, one of the possibilities is that it takes a function and returns a function. So when one of the arguments must be a function, then that function's type has to have parentheses around it. We're going to talk about that in more detail in a little while. All right, so this is the type signature at the top of function composition. We have 3 types in this one, A and B and C. And again, they could all be different types. They could all end up being the same type. All the A's have to be the same, all the B's have to be the same, the C's have to be the same. But they could be different. And flip, you see, flip takes one function as its argument and just flips the order of the first 2 inputs to that function. Okay, so these are type signatures, unlike ID and const, right? ID and const, we didn't have any information about the types in them. They could be any type at all. And same actually with function composition. But these type signatures here for, I have addition and append, these ones have constraints on them. So the A to A to A in addition might look similar to the ID function. I mean, that was only A to A. But there's a really important difference. The difference is that it has this num constraint at the beginning. And the num constraint tells us some information about what type those A's will become. It doesn't tell us everything yet. There's still some possibilities. But it tells us some information about what those types will become. When you see a constraint like this, it means everything between, I don't have a way to like highlight on the slides. Oh, I have the laser pointer, don't I? But I'd have to do it on. Huh? Well, no, when I touch them, the slide moves. I think because I'm in presentation mode or something. Yeah, see? Yeah. So I can just move the cursor over like this. So this information here is a type class constraint. So everything between these 2 colons, which is how we declare a type signature, right? So this says plus, has the type num A, And that's the end of our constraint right there, that fat arrow. A to A to A. So it takes two arguments, right, and returns an argument and returns a value of the same type as those two arguments. Addition works for a lot of different kinds of numeric types, right? It was really a surprise to me when I started learning Haskell to find out that there's more than one type of number. I think I was supposed to understand that at some point in one of my mathematics classes in high school or something, but I never really quite picked up on it because we don't really treat them very differently, right? We don't talk about them as if doing division or multiplication on decimal numbers versus integers. We don't really talk about them in high school, or at least my high school, but maybe I had a bad math teacher, as if those are different things. So it was quite a surprise to me when I started learning programming that we have to treat those differently. So we know from this, then from the type signature of addition, that it will take two types that have instances of the type class num. So the type class num is where we find is where we get our operation for addition and multiplication and several other important numeric functions. They all sort of live in this num type class. And a bunch, not all, but a bunch of numeric types have instances of the num type class. And the instance, and we're going to talk about this in more detail as well, is what defines how those are implemented for a given type. So the num has this sort of the num type class has this very general definition of addition, just that it takes two arguments of the same type and returns a value of the same type. All right, and the second one there, that's mapend from, well, it's really from semigroup now. I'm old-fashioned, so I keep saying it's from monoid. So that comes from the monoid type class, or actually the semigroup type class. And it looks very similar, right, to the addition type signature. There are lots of good reasons for that we'll talk about in more detail as we go along. And it's important to note that we could write the type signature for mapend with A's instead of M's, and it would mean the exact same thing. So the M's kind of serve as a mnemonic that we're talking about monoids, right? Or monads, because we use the M for monads too. And we use the F, we use an F for a mnemonic for functor type class. But that's all they are, is a mnemonic, right? Okay. Oh dear, we had some type signatures just run right off the page. I guess I should have checked my slides better. All right, so sometimes type signatures get to be very complicated looking, but that's okay. We just practice reading them, and then we can do okay. So this. I wanted to show you these type signatures in particular because this foldable constraint, this foldable T, that comes up an awful lot with all kinds of functions that you might not be expecting that there's a foldable constraint on. So the foldable type class is a type class that has a bunch of operations for things that are like lists. So when we Okay, I can't type and hold the microphone, can I? All right, so when we ask GHCI for the type of concat, for example, it will show up right here. And this worries a lot of people, right, when they see this constraint, because in this case, right, concat takes a list of lists, or this is how we think of it. It takes a list of lists and returns a list, right? So it sort of smashes the two layers of list into one list structure. The foldable T just makes this more general. So now we could have any of the types, this T that's in front of the first list of A's, right? This T here. This T here is the one that's constrained by the foldable constraint. And so this T here can be any of the types that implement the foldable type class. You can think of them as being list-like. They're not all very list-like, but you can think of them as being sort of list-like things. All right. And so when we see these type signatures here, which are running off of the page, and I'm sorry about that, right? We find that this applicative, we find that this applicative F appears here, and this traversable T appears here. And so this helps us keep track, right, of which types are supposed to be where. The T and the F, in some cases, will be the same type, but it helps us keep track of which operations we're using with those types, because the operations come from the type classes. All right, so another cool thing about type signatures is sometimes we can line them up like this and compare them and learn a lot of new things. So this is part of how I eventually figured out what this bottom one, die-map, this is the main operation that comes from Profunctor, and this is part of how I finally figured out what it was supposed to be doing. So if we look at the top three, for example, these are all ones that we'll be talking about in quite a bit of detail probably tomorrow, but we'll see. If we look at the top three, we can see the similarities, right? We have a functor F, and an applicative F, and a monad M, but we know that it doesn't matter that it's a monad M. It could be a monad F, right? And we can when we line them up and see, we see that at least at the end, they're all sort of doing the same thing, right? All of these are taking some function as an input and giving us a way to get from MA to MB or FA to FB. So they're all quite similar, and those similarities are what we're going to talk about when we talk about functors. And then when we compare the type signature of function composition with the type signature of die-map, we also see some important similarities. Or maybe you don't yet, because the type signature of die-map is a very long type signature. And the P here, this should actually have a type class constraint, but see, with this one I was afraid that it would run off of the slide, and so I didn't put the type class constraint, and I guess I shouldn't have on the others. But the P here is for Profunctor. So the P's in that type signature will be constrained by the type class Profunctor. All right. And if you want to see a whole bunch of Haskell type signatures lined up, you can see them here. So we did that a lot in Haskell book. We showed a lot of type signatures lined up together, and then Chris here has just taken that ball and just run with it and lined up a whole bunch of them. And it's really quite illustrative, I think, to look at them all lined up and see all the similarities between them. All right, any questions on what we've covered so far? Yes?
You mentioned a few, I would say, conventions about naming just the kind of variables, like M.
Yes.
Are there other great common known ones that we should kind of know?
In type signatures, not so much. Usually at least one of them is a mnemonic for some type class that it's constrained by, so like the F's and the M's. But type signatures tend to, the variables tend to start from A and go A, B, C. Sometimes people will use, and you'll see this like with GHCI a lot, they'll use like A1 and A2 and A3. So sometimes when people do that, they mean that A and A1 are somehow related to each other. When I'm talking about functors tomorrow, you'll see that I do that a lot when I'm talking about functors. I use like A0 and A1 and Z0 and Z1 because I like talking about functions going from A to Z instead of A to B. No, in type signatures it's usually A, B, C, and then these other weird ones like P and T and F are usually a mnemonic for a type class. But not in GHCI. GHCI for some reason uses T a lot, and I guess for type, I'm not really sure why. So, yeah.
Just let me know if it's too complex for you. I'm curious why concat, right, has default default constraint only for the outside list, not for the inside list. Do you happen to know that?
No, I've wondered that myself, and I don't.
It's kind of weird, right?
Yeah, and I don't actually know the answer. Does anyone else know why?
That's what I said. Maybe it's not too complex question.
Yeah.
Okay.
So he's asking why does the well, I'll repeat it, and that way it'll be louder for the recording. So yeah. So he's asking why the type signature of concat has a foldable T here and not also here. Like, why is it not? Hang on, something like this.
And they could be distinct, right?
Yeah.
Because it's like now the outside list you can have like a list like a tree or something, but for the inside you only have a list. Why?
He's asking why it's not something like this, where the T and the F would both be. I mean, well, they'd have to be the same, wouldn't they? Yeah. So they would have to all be the same, but.
Right.
So he's asking why it's not like. Right, why it's not like that. Why the second list, right, is not also made more polymorphic in general. And I don't know. Right. I mean, I think concat is one of them that a lot of people think shouldn't have the foldable constraint at all and should just be for lists of lists. Foldable is quite a controversial type class, so I try to avoid talking about it, particularly with beginners. It's quite a controversial type class and has a lot of controversial things in it. We are gonna, when we talk about functors, when we talk about the functor type class, we will talk some about why foldable has some of the behavior that it does, but we'll leave it for now. All right. So now let's move into talking about polymorphism. All right, so we have two kinds of polymorphism, and they are related to each other, and we sort of move from maximum generality, right, from parametric polymorphism all the way down to a concrete type. So parametric polymorphism is when there's no constraint at all on the type, such as we see with ID. So the A's in the ID type signature can be seriously any type in the universe. They could be functions, they could be bools, they could be strings, they could be anything. With constrained polymorphism, we still have variables, so we still don't know what type it is, but it is constrained to being just a certain set of types. Just types, in this case, for the abs function, it's just types that implement the num type class. Okay, so like I said, an unconstrained type variable can represent any type in the universe. And the function has to have the exact same behavior for any possible type that ends up in that slot. So with ID, right, we're taking in a value of type A, and since we don't know anything about that type, ID has to do the same thing for any given A. In this case, all it does is just return the A, whatever it's given. It's really all it can do, because it doesn't know anything about the type. All right, so if you think about it, it makes a lot of sense why, when you don't know anything about a type, why there's not very much that you can do to it. Because if you think about this ID function taking an A and returning an A, or the const function taking two values, an A and a B, and returning an A. Without knowing anything about the type, how could we get a function that behaves properly for any type that shows up in that slot? Normally, if we have values of different types, if we have bools or ints or strings, functions, IO, right? These are things that we would want to do very different kinds of operations with. They're not operations, they're not types that we all do the same thing with, right? We don't add bools, for example. We're not supposed to. We don't, you know, the function type is quite different from a maybe or a Boolean. These types are all different enough that for a function to be as polymorphic as ID is, or const, or function composition, there's not very much that it could possibly do. And particularly with like ID, where there's just an A to A, there's nothing that happens in between the A and the A that could do anything interesting to that value at all. So we don't know anything about the type, and that function has to act the same for any given type. And there is no way that it can that they can transform that value. Whereas in the signature for function composition, we go, there we go. Here's function composition here, right? In this one we see that, okay, A and B and C can still be any type in the universe. But in this one we can go from an A to a B, right? We have some function there that goes from A to B that can transform the A into a B. We don't know what it is yet, but we have something. Okay. So most operations that we would, most functions, most operations, most methods, whatever you want to call them, I try usually to, when I'm in some contexts, I try to be very careful about which one of those words I use, because they have slightly different meanings in different contexts. Like methods mean something very specific to some people, but when I'm speaking like this, often any one of those words might come out of my mouth, and I mean the same thing by them. So, so most of the operations most operations are associated with some specific type, or a constrained set of types. So they're associated with some specific type. So there are things that we know we do with Booleans. There are things we know we do with integers. There are things we know we do with strings or functions or IO values. But most of the operations are associated with some type, or a constrained set of types, such as addition being associated with types that implement the num type class, or maximum being associated with types that implement the ord type class. The ord type class is a type class for orderable things, right? So max is the maximum function. You give it two numbers, and it tells you which one is greater. So these two type signatures look very similar. I didn't line up the A's, did I? Oh, that's a tragedy. Okay, so could all of these A's, we know that all the A's in the addition type signature are the same A. We know that all the A's in the type signature for max must be the same A. Could all of them be the same A? They can be, but they don't have to be. That's right. Yep. Yeah.
It's a bit of a late question, but I'm wondering, could you have a type class for functions? Types which are functional.
Yes. But function has Also, and we're getting there, but function also has instances for a lot of type classes that already exist. So, but yeah, sure. I don't know. What would you want it? What do you want it to do? What functions would be in that type class?
Well, all the functions. But maybe you have things like some certain tuples. Construct types of tuples and certain graphs.
Sure. I think so. I don't know if it would be useful because, you know, the num type class has a whole bunch of things in it, but like it seems like as time goes on, we're getting smaller and smaller type classes, and so each one of them is more specific to, you know, just having one or two operations, and they're usually closely related. So, I mean, Monad has a few, but it really only has a couple that we care about, right? So it's, I guess monoid is down to one now, right? Monoid is down to one sad thing that's not even a function. So, but so yeah, I'm not sure that you'd want to, but you could, sure. Yes.
Does it make sense to have a type signature that goes from unconstrained A to unconstrained B, and can they eventually also be the same type as when you implement?
Sure.
And is there anything that makes sense like that, or am I just being out here?
Well, let's think about this. If we have an unconstrained A going to an unconstrained B, you want to write a function that can go from any type in the world to any type in the world. I think that would be difficult to implement, yes. Yes?
Main question about implementation. If we had a function which basically has some kind of dictionary, and for every type it would have some other type, and like for a function it would return a bool, for a integer it would return a character, and so on. And like we map all the functions in this dictionary. So what would be the type of this function returning something else? Would it be this A to B, because it would take any function and return any function, and take any type and return any type?
So you want to make sort of a big record of all the types. But people can always invent new types, and so then you'd have to keep adding to the record, right? Every time there was a new type invented to make sure that it could always go to whatever B. Is that, but you want to have like this giant record. So for any A, you have some way to get to, right? You would still want the A. So whatever the input is, you still have some way to get to any type. Wow. My, what questions we're coming up with so early in the morning. Yeah. Right. Yeah, I mean, A can be arbitrarily complex, and so I guess you could. I think you would get. I mean, I don't think practically that you could do that. But I'd like to see someone try. So, yeah. Oh, what? Yes. Oh, right now? Okay. Okay, yeah, sure. Thank you. Okay, we get to go on break already. So I feel like we just started, but all right, let's finish this slide next. So how about these two? We have the addition So here we have num a to a to a to a, right? So that's a function that takes two arguments, right? A, and returns a value of type A. Then we have monoid M, we have them append, and again, this really should be semi-group, I guess. M to M to M. And I said already that those could be A to A to A, right? If it would be monoid A, then A to A to A. So we also have two arguments of the same type, returning a value of that same type, right? So could these, the A and the M, be of the same type? Right. Yes, but they don't have to be. They're different signatures, that's right. So it turns out that actually for some types, these are the same operation. We're going to talk about those very soon, because I promised you functors, but I always have to talk about monoids. And so we're going to talk about monoids soon. So yes, for some types, for types that have both a monoid instance and a num instance, these are actually the same operation. Yes? Yes, because there are numbers that addition is not associative. So, right? Yes, there are some kinds of numbers that addition is not associative for, apparently. This is what I've been told, but like I said, I try to tell people this in every talk because it seems like a lot of Haskell talks and a lot of Haskell beginner materials, including my book, start off with a lot of arithmetic. I really hate arithmetic, and I really don't like numbers. I was a linguist, so I like to do things with strings. But yeah, what I've been told, my understanding is that there are some types of numbers that addition is not associative for, and so they're not monoids. All right, so we'll leave off there and have a break and pick this up when we come back. Okay, so has everyone gotten coffee? Well, I figured I probably better start talking again at some point, right? It's fun to socialize with everybody, but I probably have to talk some more. So, are you getting some coffee? Okay. Okay, so welcome back, everybody. So we've been talking about type signatures and polymorphism, and so we now want to compare this set of type signatures. And you notice that I didn't give these functions any names. These are real type signatures from various functions, and I didn't give them any names in part because I want to talk about what kinds of functions these could be. If you don't know the name of them, then you can just focus on the type and tell me what they might be. All right, so when we have A to A, we have the unconstrained type. So the A's have to be potentially any type in the whole universe, right? And that function is going to have to behave correctly for any type in the universe, no matter what type that A is, whether it's a function or an IO or a bool, anything. So all of these have some superficial similarity, right? They all are one argument and returning one result. But the A to A is quite special because it has no other information on the type at all, right? So what function could the A to A be? Identity. Is there anything else? 0? Is there anything else that A to A could be that will behave correctly for? Huh? But then it would have to have a num constraint on it.
Why not?
Well, because you don't have a signum that behaves correctly for bools.
It's like num bool?
No, that's what I, yeah, that's what I'm saying. So the A to A, this top one,
Okay, I think we were taking
yeah, no, we're still, sorry, we're still on the top one. Yeah, I don't have my, my pointer or anything, and so just the A to A. Could it be anything other than identity? Well, hello, coffee machine. All right, so could it be anything other than identity? Is there something else we could implement that would do the same thing no matter what type we give it?
not in a pure language, I guess.
No, right. And this is such a pure language. So, right, so A to A can just be identity. And there's nothing else we can, that's nothing else that can be.
Constant, can it be to map every object in the type to one single instance?
Well, I mean, in some sense, right, if this A, because this could be any type, so if the A was, excuse me, if the A was a function from A to B, could we do that? If A is a function from A to B, okay, why not?
I guess because you can't transform A to B if you don't know what type it is. So it's impossible, like you said, to actually write a function if you take any type and convert it in some way.
Right. So if it was a function from A to B, if A was a function from A to B, what would we be returning? Well, identity function would be returning A to B, the same function, right? So if the A's of identity resolve to a function, A to B, well, sure, I'll just type here. Yeah, you're going to give me a parse error. Yep. Okay, so if we have A to A, and if that turns into, because that A could represent A to B, but then the A's have to be exactly the same, and so what we would be returning then is not just an A value, right? We'd have to be returning an A to B. That's a perfectly good implementation, but it's still the identity function. Right? It's still, instead of taking in a single value, like taking in, say, 5 and returning 5, now it's taking in an A to B function and returning an A to B function. So it's still behaving correctly, because function is a type. So it's still behaving correctly for a value of the type, but it's not actually transforming that function at all. Does that make sense? It's not evaluating that function. It's not doing anything. All it does is just throw it out the other side. All right, and this is another thing that if you teach people, if you ever do teach somebody who's never been a programmer before, and you start teaching them about identity and const, the A to B to A, they'll have no idea what those are useful for. Just letting you know that now. I didn't, right? But people use them. People use ID and const, and it's very puzzling to people who are not programmers. So be sure that you explain that. All right, how about this one? Now we have a constraint on the A's. So we know there's a certain set of types that it could be. Not any type in the universe, right? Only ones that have instances of num, which will be most of your, what you think of as numbers. And most of the things that you don't think of as numbers, such as functions and bools and IO values, most of them do not have an instance of num. Strings don't have an instance of num. Characters don't have an instance of num, right? So this could be, this A to A can be some types from a certain collection of types, but there's still quite a few things that it can be. There are quite a few numeric types in Haskell that have instances of num. So there's still quite a few things that it could be. So what could this function be? Well, addition takes 2 arguments. This could be partially applied addition. It could be absolute value. Signum, yeah. Yeah. Yep, increment. So there's a lot of functions that this could be. So you notice how when we got a little bit of information about our types, we got a little bit of information about that A, just knowing that they implement this one type class, we suddenly have more things we can do with it. All right, the ID function really has one implementation, the A to A, with no constraints on it. That is one implementation. But num A to A, has a bunch. Not that many, I suppose, but quite a few, right? Quite a few things you can think of to do with taking a number and returning a number that's of the same type. Sure. Yeah, because you could take in like an integer and kick out an integer on the other side, and in between you could have some recursion doing some stuff to it, right? Sure. All right, so then the next one, now we don't have a type class constraint per se, but what do we have around this A? A list brackets, right? So these square brackets are special syntax for making lists in Haskell. There's these square brackets, you can't use them for anything else in Haskell. They're special syntax and you can write a list type using other syntax, but you can't use these list brackets for anything else. So this is a list of A to a list of A. Right, the A could be characters. The A could be functions. The A could be I/O values. The A could be anything. But what can we do if we know that they're lists? Reverse? Tail? Huh? Nope, concat's a list of lists. Yep. You could. Sure. Huh? We could drop some elements. Yeah. There's, tail, take, yeah. Well, take takes a number first because you have to, yeah. So it's, int, I think, to list of A to list of A. But you got the right idea, right? There's a lot of things that we can do. Even though we don't know what the A's are, there's a lot of things we can do with this because we know what the list is. Yes?
But head and tail, which popped up now, they're incomplete in
Yes.
If you run them on an empty list, they don't work.
Right.
How would you produce an empty list in that case? Is that how you would implement the function from list to list?
Well, head isn't list to list.
Yeah, that's what I mean, but it popped up as a possible answer.
Oh, okay. Yeah, no, head is... so you can write a tail that's list of A to list of A and is still safe, like, does something appropriate when it's given an empty list. But a head, you have to do something a little more complicated. So, because a head takes a list of A and just returns an A, right? Because it just returns one element out of the list. So you can't take a list of A and return the empty list for head. That's not a solution. For tail, you could. Right. Okay, so we know some things about this. Even though we don't know things about the A, we know some things about the list type. Right? We know what kinds of things you can do with lists. List has some type class instances that we can work with, so it has a lot of operations over it. But if we don't know what the A's are, then this operation has to be things that only affect the list part, right? They can affect the number of elements in the list. They can affect, right, it could return an empty list, for example, or it could take some things out. It could, like tail does, it could reverse the list, but it can't do anything to the A's, right, except for, change their order or take some of them out. But those are operations with respect to the list. Since we don't know anything about the A's, a function that's just list of A to list of A has to be, can't really affect the A's. Does that make sense?
For example, sorting, we don't need to have a place here because you need two in order
Right.
to sort the A element.
Yes.
You don't know if
Right.
they are sortable or not.
Exactly. Yes. Did everybody hear him? So sorting, this this could not be the type signature for a sort function because we don't know anything about the A's, so we don't know that they're orderable, right? If we had, say, an ORed constraint, right? If we had something like this, right? I said that ORed is the type class for orderable things. Now we know that our A's are orderable. All right, now we know that we can put them in some order, like characters and numbers and things like that, but not all types are.
Actually, for some types of sorting, you use more, like for bucket sorting,
Yes.
you use more.
Yes. Yeah, I think so. Yeah. But let's say some conceptual idea of sorting, right? You could do it just if you know that these things are orderable. But if you don't even know that they're orderable, then you can't, right? Okay. All right, then we have a maybe A to a maybe A. This is a lot like the list of A to list of A, right? We've done nothing to the A value, but we might be taking in a maybe A and returning. There are two values of the maybe type for those of you who are new to Haskell. There are two values. It's sort of similar to bool. Bool has two values, right? True and false. Maybe has two values, either nothing, just something like a false, or just A. So with this function, we could take in a maybe A and return either nothing or just A. Yeah.
One question about notation. Why is maybe A and not the same way as with number, maybe and implication A? Because num just above has num only at the beginning, implication, and maybe appears two times.
Yes, okay, because num is a type class and maybe is a type or a type constructor. And so maybe A to maybe A is really similar to the A to A or bool to bool, where we're going from a type to a type. Num A is telling us that these A's are constrained in some way, but it's not actually telling us what type they are. It's just telling us that this type is a member of the num type class, or an instance of the num type class. Does that make sense to everyone? Okay. Yes?
List syntax actually exception. We could write the parentheses from the list and after that A. And it will align with maybe A. Because it's the same.
Oh, yes. Yeah, we could.
But on the slide it says special A.
Yes. But that is like if you look at the type signature of like reverse in GHCI or something, or in documentation, it will say list of A to list of A like this. But yes, you can write the list brackets the same way we wrote maybe A. So like, because you can write it like, oops, like this, where the list then is analogous to maybe, right? The list brackets are analogous to maybe, and they're being applied then to the A. Okay, and then we have a bool to bool function. How many things could this be? Right, it could be not. Right, not. Yes. So I think altogether there are 4 implementations of this, right? Yeah. 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 I didn't say they were interesting implementations. I just said there were implementations. But bool is really, in a lot of ways, not a very interesting type, right? So, one.
What about maybe?
Hmm?
Maybe a. How many functions? I think it's a nice puzzle. About maybe. How many functions you could define with the maybe a mapping to maybe a?
Only 2.
In my opinion, infinite. I think that's a little bit trick. You could get infinite number of.
No, but because it's like with A to A, you can have only one function,
Yeah,
right?
I think you could have. Oh, yeah, you're right.
Yeah,
Okay.
because you, on the inside of it, you can only have the identity, or you can
Yeah,
have
yeah,
nothing
I was-
without anything.
I was thinking about wrapping maybe, but yeah.
Yeah, that
But
would be
it'd be a
maybe A,
different
maybe
thing.
A, right?
So, well, yeah, I mean, the A could be another maybe. But,
But we would have to on each side, right?
yes.
Regular.
Right. Right. Yep. Just like we were talking about with identity being an A to B function. So, all right. So these are very different type signatures, even though they're superficially similar in some ways, right? Each one of these things takes one argument and returns one result of the same type. Now, each one of these takes one argument, a num a list of a maybe a, or a bool. Each one takes one argument and returns a value of the same type. So superficially, these are very similar. But in practice, they are quite different because of the ways that polymorphism works. So the general rule is that the less you know about a type, so when it's, the less knowledge you have of what type it could be, then the less you can do with it. Because the function will have to behave correctly for any type that goes into that slot. The more you know about it, right, as we move down the list to bool, the more you know about it, the more sort of things you can implement. I mean, it's less so with bool to bool just because of the nature of bool, but the more knowledge we have about the type in general, the more things we can do with it. We have type class instances, and we have certain things that we know about how these types should behave, right? We know how lists should sort of behave, right? And what kinds of things we should be able to do with them. Okay. All right, so now we're going to start talking about the type system. Emphasis on system. So there are types that we've been talking about. Some of them are already in the base library, and so when you are writing standard Haskell, you have certain types already at your disposal, such as bool, and lists, and tuples, and a lot of numeric types, and the kinds of things that you generally expect to have when you have types, right? We also, though, in Haskell, we can write our own types. So you can make up a type for whatever kind of data that you have. And so we have types. But the type system goes beyond having types. Types and type classes form a structure that is analogous to algebraic structures. So algebras, or algebraic structures, are sets. Everybody understands what I mean by sets? Okay. Types are different from sets in some ways that don't matter to us right now, so just think of them as being similar enough. So algebras are sets plus operations over those sets, right? Operations that work with those sets that satisfy some laws. All right, and so the type system, types and type classes and their instances that tie them together form structures that are analogous to algebraic structures. All right, so we're going to start talking about a set or type that most of us are probably mostly familiar with, or at least think we are, integers. So we have a couple of operations over integers that behave very similarly, addition and multiplication. Addition and multiplication are both binary operations, meaning they take 2 arguments, right? So there's a number on each side of the plus sign, for example, or the times sign. So they're both binary. They're both associative, which means that it doesn't matter how we parenthesize them, right? The answer will be the same. Right, so if you have, I'm not sure how effective my gesturing is, so yeah, that's 9. And I can't type apparently. So that's going to be equal to 3 plus 9 plus 8. Right? Yes. Those should be equal, right? And I guess that we can actually evaluate that. Look at that. All right. So that's what we mean by associative, and multiplication is the same. And they both have identity elements. Does everybody understand what we mean by an identity element? There's an element of the set that acts as an identity value for the operation, meaning that it doesn't change whatever the other argument is, right? So for addition, it is 0. For multiplication, it is right. All right. You guys are on the ball. Okay. So we can ignore the differences between multiplication and addition when we want to. We can, because how multiplication and addition work is just an implementation detail, right? What we can focus on is those similarities that they have. And we can actually notice, and we'll get to this later, we can notice that a lot of other types share some operations that have those same similarities. So, for example, over the set of Booleans, there are conjunction and disjunction that are in many ways, in many important ways, very similar to addition and multiplication of integers. There are operations over sets that are also similar to multiplication and addition. Does anybody know what they are? Union and intersection, a little bit more similar to what we think of as addition and multiplication of integers would be disjoint union for addition and the Cartesian product for multiplication. That doesn't matter a great deal right now, but we notice this pattern, so we choose now to think not about the implementation details, but about that pattern, right? We care that we have a binary associative operation over some set that has an identity element for the operation. All right, so integers, like a lot of other types, form a monoid. They actually form two monoids. They form a monoid under addition, and they form a monoid under multiplication. I promised you that we were going to talk about monoids, so here we go. We'll get to functors later. All right, so yeah, we're abstracting, so we don't care right now that they actually form two monoids, right? Because we're abstracting away to just caring about the binariness and the associativity and the identity element. Okay, so we could call the operation something like, add mult, and it would have a type that looks something like this, right? We would want to constrain this to the integral type class, which are things like integers. So instead of num, we have a more constrained type. Num is a type class that has more type, that includes more types than integral does. So integral will be things like integers, right? And we could give it this type signature. It's going to take two integers or two integral, right, types and return one of the same type. So that would give us a binary associative operation, or we would want to make sure that it's associative. But it would at least give us a binary operation that's closed, meaning it returns a value of the same type. But we still need an identity, right? We need to define identities for this. Okay. Oh yeah. Oh, my little shruggy guy didn't turn out. Okay. So the associativity law that should hold for the operation can and should be tested, but is not actually enforced by the compiler. Sadly. Yeah, I didn't escape. Yep. You got it. All right. So since we need an identity element that's not enough by itself to make the algebra with integers. It's polymorphic enough to define either of those operations, but it needs an identity. So now we're going to have at least a pair of things, right? We're going to have, say, an identity for addition and identity for multiplication. And now we would have a type class, a set of operations that we could define for any type that's like integers. Okay, we would write then instances for different types, integer and int and so forth, that defined implementations for how addition and multiplication should work and what those identity values should be. But that does give us a problem. Addition and multiplication don't have the same implementation. So if we wrote an implementation of this for integer, what would the implementation be for our add mult function? Would it be, the type signature is okay, right? Because we can do, because the type of addition and multiplication looks the same. It takes two values of a certain type and returns a third value of the certain type. But what would the implementation look like? We're trying to focus on just what these two functions have in common, addition and multiplication. Right, so we're trying to abstract, but now we have a problem because we have to actually implement this function. We have to write something that ties the type integer to this generic function. And what does the implementation look like? Well, addition or multiplication, right? It looks like either of those, but we've tried to make it just one function. So, instead we'll try this a different way. We'll give our operation an even more general name and only one identity method, but we'll give each implementation its own type name. All right, so we're going to call this class monoid. A monoid is a set plus a binary associative operation that has an identity element. So it's a sort of triple of three things: a set, a binary associative operation, and an identity element from that set. In the case of multiplication and addition, 0 or 1. All right, so we have the class monoid. This is what the actual type class declaration looks like. Mempty is what we call the identity value, so it's just a value from whatever set we're talking about, whatever type we're talking about. And we have this mappend. The infix operator, which is what I usually use for mappend, is the two angled brackets, the little diamond. All right, and so now we have this very generic operator, right, that we can use to write binary associative, that we can use through instances to implement a vast number of binary associative operations that have identity elements. All right, and this also tells us some things that this operation cannot do, such as change the type somewhere in the middle. Right? If it's taking in two integers, it has to give us back an integer. If it's taking in two booleans, it has to give us back a boolean. If it's taking in two functions, it has to give us back a... Right. Whatever we've given it for the a, it has to give us back one of those values. All right, so there are definitely some things here that this operation cannot do. All right, so the instance that I've been talking about is the piece of code that ties a type class declaration, such as this one. Right, this is the type class declaration that ties a type class declaration to a specific type. A type class declaration is as polymorphic as it can be. So it's as generic as it can be so that we can use it for as many types as possible. And there are lots and lots of types that can implement the type class monoid. An instance gives the implementation for a given type. So then we have an instance declaration. And we say instance monoid, whatever the type name is, and then we write the implementation for that type. Okay, so these are defined in, because they're not in Prelude, so like if you open up GHCI, these will not automatically be available. You have to import data.monoid. But we have this new type called product. Product is sort of wrapper around, or a sort of, yeah, it's a different name for different kinds of integer types. And we see here the instance, right here, right? We have an instance, it's num A. Yeah, and there's the semi-group, because I keep forgetting that this has happened. When I started learning Haskell, when I started teaching Haskell, this had not happened yet. It still said instance num A, monoid product A, and now they've just pulled the rug out from under me. All right, so semi-group seems like a very different thing, but it's really just a monoid that doesn't have an identity. So it's just a binary associative operation. So what this is telling us is that because this mappend operator is actually defined, I have 10 minutes. 5 minutes? That's impossible. Okay. So what this is telling us is that whatever this A right here is has to have an implementation of num. Right? And this operator actually, I've been telling you that it lives in the monoid type class, and it actually lives in the semi-group type class. And then the monoid type class, actually all it adds is just the identity element. All right. And we're not going to worry about this coerce thing, which is really not a big deal. But then here's our A to A to A. And here it's telling us that this, right, mappend operation for the product type is the same as multiplication. So now we have an implementation for you know, integers, but by a different name, right? Or for numbers, really, but by a different name. All right, and so then we would have down here, here's the monoid instance, and you can see that all it defines is just mempty, just the identity value. And that is a product 1, right? Because that is our identity value for multiplication. Okay. Yes? Yeah. I should have just taken that out because I didn't want to talk about it. But I didn't notice it was there. Yeah, no, the N is not. You're waiting for me to explain that more.
Maybe should be instance num A, num N.
Yeah. Yeah, but I don't think you can put that constraint in there, can you? The constraint on the N. I don't think you can put that in an instance declaration because the N isn't part of the type.
The N has an integral constraint on it. It's a constraint on S times.
Right. Right. Yeah, so you can't put it up here because the constraint that's here has to be for this type, but it would be on this actual function, like on the type signature of this function.